Hello again. The final piece of our electron arrangements study has to do with something called Lewis dot diagrams. Lewis dot diagrams are by far the simplest, most compact, convenient way of expressing something about an element's electrons, but the key word there is something. The thing about being concise in the case of a Lewis dot diagram is that they're very, very brief, they're very small, they don't show very much, they don't tell the whole story, but they tell, in a lot of ways, what's the most important part of the story. And that has to do with how that element's atoms then are able to form bonds, and sometimes how they're not able to form bonds based on their Lewis dot diagram. So a Lewis dot diagram is going to emphasize the electrons that take part in bonding and sort of leave all the other electrons of that element's atoms sort of in the hindsight, and they aren't included in what we'll do with our Lewis dot diagram. And you'll see what I mean by that in just a minute. So Lewis dot diagrams were developed by an American chemist, and I have that here in underlined italics and an exclamation point because there aren't, up to this point in history, a lot of American contributions in the chemistry that we study in first-year chemistry. And we don't do nearly as much with atomic theory, history, and information about how the atom came to be understood in its somewhat current picture as of today. But when we used to, there weren't any Americans involved really in that story, as we talk about it in our class, until we got to Lewis. And he was much later in the story than a lot of people from Europe, all over Europe, and the contributions came from people from all over Europe and even places like New Zealand. So Gilbert Lewis, was a very important contributor to our understanding of chemistry with something called Lewis dot diagrams, Lewis structures, which are built from Lewis dot diagrams, and also things like Lewis acids, which we get into more as we look into more advanced chemistry concepts. So Lewis is an important figure in chemistry, and he's an American. He did this work in the early 1900s, so a little bit over 100 years ago. And these Lewis dot diagrams are very short, sweet, and home to eat, but get to the point of something that can be useful in ways that the other electron arrangements that we've worked with really couldn't be. They're just not as convenient in the ways that these are. So here's what Lewis dot diagrams are in summary. And what they basically are is they show the elements abbreviation, so that's the one or two letters from the periodic table that we'd find as the abbreviation for the element. And then we also add a dot for each of the atom's valence electrons. So each atom has a certain number of valence electrons. We include a dot for each of those valence electrons. Here we see defined what a valence electron is, and you might have heard of this term before, but if it's been a while or if it's new to you, this is a very, very important idea. The valence electrons are the electrons that are found in an atom's highest energy level. And remember, we've been talking a lot about energy levels, 1 through 7. So whichever one of those is the highest or outermost energy level would be the electrons that we would focus our attention on when it comes to drawing or writing a Lewis dot diagram. The valence electrons are the ones found only in the highest energy level, be that 1, 2, 3, 4, 5, 6, or 7. Why do we focus so much on the valence electrons? Well, these are the electrons that it says here, are involved in forming bonds, and which is sort of the same way as saying another thing here. They're the electrons involved in determining the element's properties. So many of an element's properties are functions of their electrons, valence electrons. How an element forms bonds is another way that we understand its properties, and that's all a lot having to do with the number of valence electrons that an element has. It's important to know that no atom will have more than 8 valence electrons. No atom of any element out there will have more than 8 valence electrons. So that's the maximum number. And when it does have 8, we call that an octet. So this idea of 8 valence electrons, we're going to be talking a lot about over the weeks to come here. The idea of an octet, and that being 8 valence electrons. When an atom does have 8 valence electrons, we call that an octet, or more precisely perhaps a full octet, because that's the maximum. It's also sort of a fullness when it comes to having 8 valence electrons, and there's also a certain stability that comes from having 8 valence electrons that none of the other potential numbers of valence electrons will have. Okay. That's what it looks like. So let's look at one. If we look at carbon, carbon has electron configuration 1s2, 2s2, 2p2. We could write electron configuration for a short element like carbon relatively quickly and hopefully pretty comfortably by now. We've looked at an orbital diagram for various elements, and for carbon that would look like this: 1s2, 2s2, and 2p2. And you see I've got circled here the 4 electrons of carbon that are considered its valence electrons. Remember, we have energy level 1, and then we have energy level 2. And both 2s and 2p, all of these electrons, are part of level 2. So since both of these are part of carbon's outermost or highest energy level, those are the valence electrons. Those 4 valence electrons. 2 here and 2 here. Or as we see them drawn, 2 here and 2 here. Those 4 valence electrons make up the ones that are part of the Lewis dot diagram then for carbon. And what's that going to look like? We'd have carbon, so we'd use C, the single letter abbreviation for carbon, and then we'd simply put a dot around that abbreviation, 1 dot for each of the electrons in the valence level. And so each of these 1, 2, 3, 4 electrons is represented here as an electron dot, 1, 2, 3, and 4. Now where we put them sort of around the carbon there isn't quite as specific as having the right number of them, but typically you want to sort of go around, distribute them sort of evenly. There's really not a hard, fast rule that makes it right or wrong in this way, but we sort of want to spread those electrons out. And the real reason as to why, it's you can think about it like Hund's rule. We want to sort of spread them out and balance them, but probably more importantly, it has to do with molecular geometry and how an atom, how an atom like carbon will form its bonds based on where those electrons are getting involved with other elements. Carbon will form bonds that orient themselves in 4 different directions, and so we put its 4 valence electrons, which are part of forming its 4 bonds at the most. We put those electrons pointing in 4 different directions. So that's the idea of a Lewis dot diagram. That's it. It's the carbon's C from the periodic table and 4 dots for its valence electrons. Now, to get the number of valence electrons, you may have to sort of think about the electron configuration at first. You may have to think about the orbital diagram. And the ones that we're going to do Lewis dot diagrams for in terms of our practice here to get started are ones that you've already done, either electron configurations or orbital diagrams for. So let's jump over there and look at some examples, the ones that we've been looking at up to this point from our previous practice. So hopefully by now you've done all the electron configurations on this page and all the orbital diagrams on the next page. All I'm going to do is go through and do the Lewis dot diagrams to accompany the elements that we did in the previous video examples for both electron configurations and orbital diagrams. And hopefully you'll have a sense of that then. And we'll maybe throw in one more so you can sort of see what it looks like when we do get to 8 valence electrons. So let's take a look at this. As far as magnesium then, if we look at magnesium, its electron configuration here at the end was 1s2, 2s2, 2p6, and 3s2. Right? We wrote that up here in our 2 videos ago as we first started looking at electron configurations. So if we kind of focus our attention on that, okay, here at the end, I'm just going to take a look at this electron configuration here. The valence electrons will be the ones in the highest energy level. So you want to simply look at that electron configuration and identify which ones are in the highest energy level. So we have electrons here in level 1. We see 1s2. So that's here. Pardon me, I thought I had my pen turned on and it's up a little bit behind. So we have level 1 electrons, we'll have level 2 electrons, we have some more level 2 electrons, and then we have some level 3 electrons. And notice I'm not paying any attention really to S's and P's at this point. I'm just looking at the big numbers because when it comes to valence electrons, we're focusing on the highest energy level, not necessarily caring as much about the sublevel. So levels 1, 2, and 3 have electrons in them for a magnesium atom. Level 3 is the greatest energy level of those. And so these will be our valence electrons, these ones right here. They're in our outermost energy level. They're in the highest energy level. These are our valence electrons. How many are there? There are 2. So there are 2 valence electrons in an atom of magnesium. Those would be the 3s electrons, and there are 2 of them. So if I went to do the Lewis dot diagram for magnesium, I would go with Mg. And then to show the 2 dots for magnesium, just put those 2 dots in here like so. And that's the Lewis dot diagram for magnesium. You probably, if you don't remember doing these before this, you might remember doing them once you get started doing a few. I'm guessing you maybe have done Lewis dot diagrams somewhere along the way. And the good news is, if not, they're really quite simple, especially if you've already done electron configurations and orbital diagrams, in which we've already done. So. All right, so that's magnesium. Let's take a look at titanium. So the next one that we had done as an example here a couple of videos ago was titanium. If we look at that configuration, which we've kind of got it by color, so I'll stick with those colors. We had electrons in level 1. We had electrons in level 2. Pardon me. I switched colors, but it didn't switch colors. Level 2. We have electrons in level 3. And those are a few different places. We have 3s2. We have 3p6. and we have 3d2. Those are all part of level 3. So I could look at this and say that in titanium there are 2 and 6 and 2. There are 10 electrons in level 3 in 3 different sort of sublevel shapes, right? S, P, and D. But the ones that we're interested in here are these level 4 electrons, because level 4 is the highest energy level in an atom of titanium that has electrons in it. So these are our valence electrons, these 4s2 electrons right here. And so titanium would have 2 valence electrons, looking at its configuration. So for titanium, I would go Ti for titanium, and then to show those 2 valence electrons, 2 dots, just like so. So both magnesium and titanium, we could say by these definitions, would have the same number of valence electrons, 2, and they would actually be of the same sort. In magnesium, there are 3s electrons. In titanium, there are 4s electrons. But we'd be identifying the same sort of electrons, at least in terms of the region that they occupy, being a sphere in shape in those s examples. Okay. Let's take a look at selenium. We've got selenium down here at the bottom from our examples from a couple of videos ago. And again, we'll kind of focus on the same sort of thing. I'm going to go ahead, I think, and clear out my notes here, just because we don't need all that for our work here today. So I'm going to take care of that, delete that all out of there. And then I'll also sort of maybe try to clean this little guy up at the end. So I'm going to just sort of rewrite this part. We had 3d10 and we had 4p4 at the end of our selenium configuration. And we can glance this over now as you go through and identify. We've got level 1, we've got level 2, we've got level 3, we've got level 4, and that's where it ends, right? And remember, selenium is in the 4th row of the periodic table. If we go down the side and number those S block sections, 1 through 7, selenium is in the 4th row of the periodic table. So that means it has electrons in 4 energy levels. And for selenium, these are the valence electrons then. These are valence and these are valence. All of these, right? All of these electrons here and here are part of level 4. And that's our outermost valence electrons. 6 electrons in the valence level. Okay, we have 6 there, S2 and P4, for a total of 6 valence electrons. So if I was to draw selenium's Lewis dot diagram, I would go for Se. I might draw my dots in by going around once and then putting the other 2 in sort of wherever the heck I'd like, something like that for selenium. So 6 valence electrons for an atom of selenium. So you have to pay attention in those orbital diagrams to recognize, or rather in those electron configurations, to recognize that it isn't always just the very last thing that we write down. It could be that level 4 is split up in a couple different places, and all of those are still part of level 4. They're in different sublevels, but they're all still part of the same energy level, and that's what defines those valence electrons for us. All right, let's look at the other side and the examples that we've done from the other side of that same page. Take a look at sodium and nickel. They may be easier to spot, they may be harder to spot because there's a little bit more going on in terms of finding those valence electrons in these atoms. So it's up to you. And as you do practice on these, get a little bit of a practice under your belt, I think you'll find that valence electrons and Lewis dot diagrams pretty quick. Knock these out in just a second or two. So sodium, level 3 is the highest energy level, right? We have level 1, we have level 2, S and P, and then we have level 3. So these are my valences here, and that's just 1 electron. So in 3s, there's 1 valence electron, and that's just it. Just the 3s, a single electron. So for sodium, I'd go Na, give him 1 dot, just like that. And then for nickel, the highest energy level is level 4. We have 1s, we have 2s and 2p, we have 3s, 3p, and 3d. But the highest energy level that has electrons in it is level 4, and that includes all of the 4s electrons. There aren't any 4p electrons like we had with selenium, but nickel does have 4s electrons, and it has 2 of them. So these would be its valence electrons right here. 2 valence electrons in an atom of nickel. And so if I was to write down the orbital diagram, or rather the Lewis dot diagram for nickel, Ni, and then my 2 dots here. That's the idea for our Lewis dots. So let's look at one more where we do get into a situation where we have a maxed out number of 8 electrons, and that would be down here on number 19 with argon. So if I was to go to my periodic table and do what we've been doing with my electron configurations or my orbital diagrams, and since this is orbital diagrams, we'll go ahead and stick with what's on this side. We'd have 1s2 for our argon. As always, we start with 1s2. We'd have 2s2. We'd have 2p6. That's that set of 3 orbitals with 6 electrons in it. And remember, argon has 18 electrons total, so we're definitely going past this. If you look at your periodic table, you would probably say and identify that argon ends with 3p. That would be the ending of its orbital diagram or its electron configuration. So that helps me to know how far to continue. I get to 3p and then I'll stop. So the next one after 2p is 3s. That gets me the first 12 electrons. And then argon's 18 electrons, the last 6 of them then are part of 3p. So here's sublevel 3p, and argon is way over there at the end of the 3p part of our periodic table, and so that would represent it having 6 electrons in its 3p sublevel. So if I count up all those arrows, those are 18 electrons. But as far as our valence electrons go, the highest energy level is level 3, right? We have 3s and we have 3p. Those are the highest energy level valence electrons. So all of these electrons here would count as valence electrons in an atom of argon. So this is an example where we would have 8 valence electrons. And so my Lewis dot diagram would be argon with 8 dots. And you'll never get past 8 if you're doing your diagrams right or your electron configurations right. If you're looking at them correctly, you should never ever get past 8. So if you find yourself writing a Lewis dot diagram that has 12 or 13 or 14 or 11, some sort of odd number greater than 8, you've done something wrong. You've overlooked something. You've maybe made a small mistake. So if these are called valence electrons, just sort of for the record then, we would sort of identify these other electrons here prior to the valence electrons. All the other electrons that aren't valence, we would sort of identify those as what we call the core electrons. I'm not sure that's a fully official term, but it does kind of give us a sense of where they are. They're not in the outermost energy level, so they're in the core of the atom, sort of the interior of the atom. As far as those different energy levels and the sort of distances from the nucleus, the core is surrounded by the valence electrons. And those core electrons serve a purpose. Those core electrons are part of the configuration. You couldn't do without them. You can't just have valence electrons. Even though they don't get to be part of the Lewis dot diagram, they're important because they sort of fulfill Aufbau. Right? We can't get to 3s and 3p for an atom of argon if we don't first fill 1s and 2s and 2p according to the rules of the Aufbau principle. So those core electrons on the inside surrounded by 8 valence electrons in this case. And we might get to getting to some questions here in the coming days where we'll emphasize the core electrons in terms of understanding them and accounting for them a little bit as well. So they'll get their moment, but the valence electrons are by far the most important elements, the most important electrons in an element. They serve the most useful purpose and they have the most dynamic sort of function when it comes to understanding how an element behaves. As we get a little further into bonding, you'll understand Lewis dots more, but for now at least, go through on all of the remaining elements on this page, front and back, and see if you can't add in Lewis dot diagrams like we've done for those. Well, the 5 that we had as examples, and we've also added argon, so we've got 6 of them done. Go through, and once you've written out the electron configurations on this side, or the orbital diagrams on this other side, make sure to go ahead and add those Lewis dot diagrams with the correct number of electron dots, and then we'll take a look at the whole thing with all 3 types of electron arrangements shown once you're done, and the key will be posted. Thanks for your attention. Until I talk to you again, be in touch if you have any questions, and I'm glad to help you out. Have a great rest of your day, and we'll talk to you soon.